approaches for the semantic segmentation. We also reviewed several data science competitions for semantic segmentation. And another topic I wanted to cover is to some real life problems that were partially solved with semantic segmentation and other neural network based approaches. So this task was at the time I were the computer vision team lead in Rambler company. We had acquired several cinemas like from Latino and Cinema Park at the time that had over 700 cinema halls. And one of the tasks that we needed to solve is to analyze our audience in the cinemas, so the social and demographic classes. So we wanted to count the number of men, women, and children on each cinema scenes to analyze and to report for our advertising companies. So as we get better reports and more details on our audience, we will get the more money budget for the advertising in our company and not the others. So as we could, for example, just use the tickets sold or the shots from the tickets booth to analyze the future audience, but this is quite inaccurate. So for example, just using the tickets information from the website will give us the 10% error because some of them are not registered at the last moment before the cinema start, before the movie starts. And as we just, for example, use the website audience analysis, then the demographic distribution would be skewed. For example, the man can buy the tickets both for him and his woman. The mother can buy tickets for the whole family. So we can't analyze the audience based just on the people who buy the tickets. But as we have the cameras in those cinema halls, we could use the image from those cinema halls to analyze it in post factum or even the real time to have the real time information on the audience and to plan the advertising before the movies accordingly. So the idea is we have the CCTV security cameras that are located above the cinema screen and targeted at the cinema audience. We can use those grayscale infrared images to count all the people sitting there. But the problem is that this is very real life problem. And we had not so usable data as we have in those fancy data science competitions or in those public data sets like COCO, Cityscapes, and others. When we have the ideal data, we have the ideal labels, and we just create some complex models and train on this standardized data. But for this real life problem, we need to create the data by ourselves, and we need to overcome all the data issues that we have, like the one shown in this picture. So the data is very diverse in terms of the cameras, in terms of the lighting. So we have different data qualities. So for some cinema halls, we have very bad quality images. For some, the resolution is quite great, the lighting is quite great. So these two images actually are even from the same hall, but we have different image quality because of the different lighting that was at the time for those images. Also, we have diversity in terms of the number of people we need to count. So some some movies have the big audience, some movies had very small audience, and we need to create models that will count good for all those cases. not to miss any person and not to misclassify the persons in the audience. So we have very diverse quality in lighting, as I've said. So this is also these are different cinemas, but we have uh, several examples of the data issues we had for those tasks. So the lighting somehow can be directed into the camera itself. So it had some issues. Or somehow, while we had installed the camera, we didn't turn on the infrared lighting at all, and we had issues like on the right pictures, and we need to contact the cinema personnel to adjust the camera to improve the position to avoid some lighting issues and so on. So this is just the real problems of the real life data science that we need to compete. And as for the data, as we need to count the people, so actually we really need to count the people and not the places taken in the cinema. So this is, for example, the data. Then we have the 4 places taken in that row and only 2 people present in that row. And we have not only standardized places to rely on, so the people can be in different places and different poses. So we have some doubling problems, as we called it, where we need to classify 2 people that are actually occupying only one space. So everything can happen in the movies. So the first approach we had was actually the semantic segmentation, but before we want to apply the model, we need to create the training data. So as we have only just raw images, we need to have the labels for them. And this is the real task for data scientists. We actually needed to use their raw images and some techniques to create the data just purely based on the grayscale raw images we had. So we used some very cool techniques like using just paint or Pinta in this case. And we needed to label all the raw images we had, hundreds and thousands of them, to actually have some labels data to train our models on. So we started from just using the manual um, paint labeling, but then we transferred to some custom build tools just for this task. So we create some internal service so where everyone can go to it, and he will be shown the example image and some tools to just places the colored points to classify the audience in this shot to uh, have more data for the training in the end. So the first approach was actually based on the task that I've mentioned in the beginning of the lecture. There was a task for counting the sea lions that were placed on the island and shot from the airplane. And I said that there were the approaches based on semantic segmentation where we could create the heat maps, the probability heat maps, and count the local maximas to really count the number of objects that we needed on those shots. So when this project with cinema was started, it was just the time when that contest for counting sea lions on the islands ended. So I just reused the code and the training pipeline for that task to apply it to our task of cinema headcount. So this is the example of probability map that was output from trained LinkNet model based on the data we had to create the true labels. So as we had some labeled images, we converted all those points placed into some form of circles, binary circles of white color on the black background, and we used it as the true semantic map for training our model. And so this was the probability outputs that look like this. So white color is actually the probability is close to one, and some intermediate probabilities they're colored blue in this example. So we could see that for this probability map, the counting of the heads is quite easily because they're easily distinguishable. But as we've seen earlier, there were quite different lighting scenarios and the camera view and angle scenarios. So actually, of course, we had lots of problems with those hard images. But as for some of the cinema halls and some of them, we had quite well quality like this, where we could easily um, distinguish several people one from another and count them. And after that, if we wanted to have the social and demographic classification, not only head count and people count, we could just crop the regions for each of the head we found. We could apply some just generic classification model like ResNet or something, and to attach all the SOTSDEM classification labels for each of the person we found on the image. And after that, we just sum up all the data we have, and as the final output, we had the predicted number of men, women, and children on that particular image, the input image. And as we crop the regions, so we had the pictures like this, and these images were fed into the classification models we've trained, and for each of them, we had the probabilities for this particular region being the children, some female or male person on that image. And after that, we just counted all the predicted labels to sum up them. And as the result, so we had some demo like this. So we found the head locations, and based on the head locations, we could create the bounding box for this place, because for each place on the image, we actually know the scale of the image that could be defined by some interesting trick. So we applied the autocorrelation function on each horizontal line on the image. And autocorrelation function, the first local maximum of autocorrelation function will actually show us the width of the chair on that row. And so based on this number of the width of the row, we could adjust the size of the bounding box for each place on the image. So as we know, the width of the chair for each vertical coordinate, we could create the bounding box based on the vertical coordinate of the head we found on the image. So we could adjust the bounding boxes for every row on the image. So as the result, for each image, for each row image, we created these bounded boxes with all those classes and accounts and total amount of people in this audience. And after we created this model, we had to verify it somehow with some external auditory, and the special people came to several cinema movies, and they counted the people on the exit of the cinema hall, and then we uploaded them our predictions, our output of our models, and they compared our output of a model with the counts that they had on the cinema hall exit. And the total quality was so that the accuracy of total counts was almost 100%, and the accuracy of adult audience classification was more than 90%, and the quality of counting the children in the hall was about 80%, but this was because some the children audience is hard to count on the images because this is the type of audience that can't be like stabilized on the image between different shots during the movie, because they really can't just sit in one place more than like for 5 or 10 minutes. And there are even several cinemas that we had that had, for example, playground on the in the cinema, and that playground was on the camera, so some children just not only seated in the chairs, but they used those playgrounds to play, and that was really hard to classify and to count correctly. But the main audience that was adult, the quality of classifying it was very good. So we continued with our models, and actually after some time we had almost all the 700 cinema halls that were analyzed every night based on the data we had during the day before, to count, to classify, and to analyze all the audience we had during the previous day. So this is all, I think, for the more lecture part of the lecture, and now we will transition to the Jupyter notebook. But it also will be some kind of lecture. I will describe you some applications of semantic segmentation using the PyTorch. I need some time to adjust the screen sharing, so I think I'll be right back in several minutes. Okay, so I've switched to the notebook we will discuss today. And this notebook also contains the home task for you, and this notebook will be available in all the lecture repos. And I think it will be updated in nearest days. So the home task for you will be up before Monday. Okay, so the last topic for the lecture is the actual semantic segmentation applications based on the PyTorch library. So we will discuss today how to build and train semantic segmentation models with PyTorch or Torch library. Okay, so we will use Torch and Torch version. That is the last, the more recent version of Torch and Torch that is 1.6 and 0.7. So to create some models and train them, everything starts with the data we need to have. So for that, we have a dataset class, and that is abstract class in Torch utils. So this is abstract class, and all the classes that inherit the dataset, they need to implement the getItem method, len method, and add method that is already implemented by the dataset. So it's not purely abstract. So actually, getItem method is just the indexing with square brackets. So the dataset and all those datasets that inherit this abstract class, they had to action like some array, because they need to support indexing, and they need to support the len method, so we can use the len from the some dataset object to get the total length of this dataset. So for example, one of the classes that implement this dataset abstraction, it is, for example, image folder class that is can be found in Torch library. For example, this image folder can be used to create a dataset object based on the ImageNet folder we have. So for ImageNet dataset, we just create the image folder object, and we provide the path to the ImageNet root that in its order has the train and validation subfolders. and for each class we have another subfolder. So actually we could create the dataset object based on this image folder class for each dataset that has this structure on our computer. So we have the some kind of dataset with trained subfolders, val subfolders, and in them we have subfolders for each class we have. So for example, ImageNet, the common subset of ImageNet has 1,000 classes. There are also variations with 5,000 classes and 21,000 classes, but the ImageNet with 1,000 classes is the most common for pre-training neural network models. So for example, let us create the dataset class for the simple dataset entries, like we have some text file with the image paths and some labels and the space between those paths and labels. So we create the text-list dataset. So the init method, so the constructor has the path property and some optional properties that are derived actually from the image folder implementation that I used to create this text-list dataset class. So as we found the images from those text files, so we have some classes that are used from as the second entity in each line of this text data. So we have the transition from class to indices of those classes. We have some transformations for our images, and we have the loader for loading those images. So the default loader that was taken from the torch vision, it is actually uses either PIL library or some other libraries that you can use. For example, we could use also some OpenCV loader to open our images. And we need to implement getItem method. So it takes index as a number as its parameter. We have the path and target from each entry we have stored in self images parameter. So we have target as a number for our training. So we convert the real target as the string like cat or dog and to the number. Also, we load the image from our path and we apply some optional transformation to the image before passing it to the next stage. So actually this dataset is used to index over some dataset with images and classes and to output those images and classes. For example, we could create this sample file that will look like this. And we use this file to create the dataset object. So we see here that we have 4 entries in the dataset. So we have classes stored in our dataset object that are cat and dog. So we have a list of images. So each image is actually the path and the label for that image. So as we apply the len method, we could use the len operator to get the length of our dataset. And if we use the indexing, we actually will have the error because there are no such image in my TMP folder. Also, there are other examples of some predefined datasets like image folder that we've mentioned earlier. They could be found in the dataset examples of touch vision documentation. For example, we could use the MNIST dataset that is for classifying digits, grayscale digits from 0 to 9. So actually, the MNIST dataset class implementation of touch vision, it also contains the functionality to download the MNIST if you don't have it. So let us create the MNIST. So we show that we need to download it, and we need the training subset of this MNIST dataset. So we actually see the output that the download has happened. So now we can see that there are 60,000 images in this dataset of some digits. We could use indexing to get image and target of some example. So this is number 5, and we can show the image we have. So actually we see that this is the grayscale image, size 28 by 28. And if you wanted, we could train the model based on these images. And as a home task, you will need to implement your own dataset. So you need to create the dataset that takes the list of URLs as the objects, and when we iterate over those dataset, we get the images. So this dataset, it gets images by the index, and you should demonstrate that it actually works. So as we've created some custom dataset, you've seen that, for example, in this class, we had the transform parameter that is quite common in all the custom datasets you will implement. For example, in ImageNet, there is a transformation that is used before passing the images into the network. So we need to normalize the images, RGB channels, using the mean and deviations of the ImageNet datasets, and pass it into the image into the network after that. So to use such a transformation and to create such transformation, there is transformations in Torch Vision library. So actually there is a module called transforms in Torch Vision. For example, the most simple transformation that there is needed is to tensor transformation, because as we need to pass our image to the to any neural network takes torch tensors as inputs, but we have only images, so we need to convert those images to tensors, and for that we have to tensor transformation from Torch Vision transforms that transforms any arbitrary image inputs that unsigned int that has unsigned int numbers from 0 to 155, and we transform it into the real domain tensors with the numbers from 0 to 1. So this is just the normalization and transformation to tensors that is heavily used for training any neural network models. So we could create the two-tensor transform like this. And for example, we can take the pill image at the first example from NIST. And we take image. So NIST 0 has both image and label, and we need only image. We apply the two-tensor transformation. So the TH image, it will be the tensor that we can analyze after that. So we can see that TH image is some tensor with this size, and minimum and maximum values are 0 and 1 respectively. For example, as I've mentioned, for ImageNet training, or for using the pre-trained ImageNet models, we need to use the normalization for ImageNet dataset that looks like this. So we have some mean values and STD values. Actually, these mean and STD values are not computed on all the ImageNet dataset, but on some predefined subset on the ImageNet dataset that is lost in time. So there is actually an issue on the Torch Vision library how to reproduce these exact numbers, and the author of the Torch Vision and Torch and the ResNet implementations earlier in pure Torch based on Lua, not on the Python. He don't remember how he got those numbers, but actually these are the numbers that are widely used in all the ImageNet training procedures. And if you want to use the pre-trained models on the ImageNet, you also need to use this normalization to have the meaningful predictions. So if you want to train on ImageNet or use the pre-trained models, you could create the transformation that use this normalized transform. And to create the complex transformations, we have the transforms compose module that can be used to create the complex transformation like this. So we can um, use, for example, for our minist objects, we could use the cropping the center of size 16 pixels and transform them to tensor after that. So if we use this transformation, so we will get the center crop of the image and it will be converted to tensor, and to convert the tensor back to numpy array, we need to apply the numpy method for that. And to create the custom transformer, you just create any arbitrary class that implements call methods. So all that transformation must do is to able to be called via the as function. So we need to implement the call method. So we could just use the call the transformation with those braces like this. And actually, you could have some in constructor as init methods. For example, if you want to implement the horizontal flip with some mode defines if we actually need to do the flip or not. And if you call this horizontal flip, then we will transpose the image if the mode is 1. And if the mode equals 0, then actually we do nothing. And for another examples of predefined transformations, you can look at the Torch Vision documentation of the transforms submodule of that library. Also, in real life and real cases, and in some data science competitions, people not only use those predefined transformations and create some transformations by themselves. There are several libraries out there just for the transformations of the images. Maybe some of the most popular is for now, it is Augmentations library. That is, for example, was heavily based on some custom augmentations that were created for that Caruana competition I mentioned in the lecture previously that were held 3 years ago. So this is the next generation of those transforms. And this library is heavily used now in all the competition pipelines and also in some production pipelines in the real applications. Also, there is some other examples, like for example, Image AUG library that heavily uses the OpenCV images and transformations. And I think you can find some other examples of the transformations. So as another part of the home task, you need to implement the default transformation group or the dihedra group. So this is the transformation that is heavily used when you create the training pipelines, for example, for satellite images, because if you have some satellite image and you, for example, make a horizontal flip of both image and the mask, then you will create the valid example, the valid labeled sample that is not present in the training dataset. Thus, you can easily enlarge the size of the dataset you have for the training without some augmentations that lose the information. So you will get just the new valid example for your dataset. And as for several datasets, typical datasets, for example, if we just get the ImageNet, there is no need to vertical flip in the image because that makes no sense. So, and you only can, for example, make a horizontal flip that makes sense for general applications. But as for satellite images, you could do any flips and it will make sense for you and will get more labeled samples for the training pipeline. And actually, if you use the default transformations, you could enlarge the dataset size by the factor of 8 if you implement it correctly. So one of the part of the home task is to implement this random default transformation and demonstrate how it works on the MNIST images we had earlier in this notebook. So as we've implemented some and reviewed some dataset class that we need to implement to have the interface for accessing dataset. Actually, the dataset semantics is very useful because the touch vision library has additional abstraction that is called data loader that creates the iterator that you can iterate over, and all the transformation you have, they will happen in the background. So for example, if you create the data loader with some batch size of 16, and then on each iteration, iterating over this loader, you will have the batch of the images with the batch size of 16, and you can use this batch to pass into your training pipeline, to your networks. And while some magic will happen on the training stage on the GPU, the data loader in the background will prepare you more images to concatenate them into tensors for the next iteration. So actually, your GPU ideally will be loaded all the times, 100% of the time, and will be loaded by 100% of the computations, while all the transformations for the data will happen in the background thanks to the data loader, using all your multiple cores of your processor. So for some small images and some easy data sets in terms of the image sizes and transformations like ImageNet, so most of the modern GPUs and CPUs, if you train ImageNet, your GPUs will be busy 100% of the time, and the CPU will be only you will use only several cores out of 4, 8, or 16 cores on your computer. So to create a data loader, we need to have some data set first. So let's use some NIST with some transforms. For example, just to tensor transform. And to create a loader, we use the data loader constructor with the first parameter. It is the dataset we use, the batch size we have, the flag whether we need to shuffle our models. For example, if we have some validation step, then there is no need in shuffling the data loader because we just sequentially use all the images we have in validation. But for the training, the shuffle is quite useful. Also, we specify the number of workers. So this is the number of parallel processes that will transform your images to form a tensors and form a batch in the end. So, for example, if you have 4 cores, it is meaningful to use 4 workers. If you have more number of more cores on the computer, you will create more workers. And for the shuffle, I have the shuffle note here. Because if you have not only some classification models or some segmentation models, if you train some more complex task, like for example, for facial recognition, where you have some complex loss functions, and you don't need only to iterate over that data set in some random way or some sequential way, you actually could create some more complicated sampling scheme to sample only hard images, only hard examples on each epoch or something like this. So actually shuffle is the basic function, the basic parameter to just randomly shuffle all the images, go one by one. But if you need to implement some more complicated scheme, then instead of just shuffle equals true, you need to implement your own shuffler, your own sampler for the dataset. But this will not covered in this topic as for now. And also, for example, for not skewing the training pipeline, if you, for example, have the number of images not divisible by the batch size, you can, for example, just drop some last images to not form the skewed batch, for example, of size 1 or 3 or something like this, and not to blow up the loss function, not gradients or everything that you have in the training process. But for the validation, you could avoid this drop last parameter and just iterate over all the images we have in the validation subset. So, and as for usage, so you can just iterate over this loader we have. So the loader will output us all that the dataset had in the form of batches. So for example, the MNIST dataset will output both image and target for it. Then if we use data loader for that dataset, then on the output, we will have the images batch and the labels batch. And if we iterate over it, so it will happen like this. So you can see that we use the TQDM loader that heavily uses the total number of images, so we can see the progress bar and the end of it. Because the dataset, as we mentioned earlier, it must implement the len method. So when we create the TQDM wrapper of that loader, we will know the total number of batches we need to iterate, because we know the total number of dataset samples. And as we have the batch size of 16, we had the total number of dataset samples as 60,000. Then we have the 3,750 iterations for the training. So we have some examples. You see that images is the batch of size 16, and we have one channel images size 28 by 28. And the targets is the tensor of size 16. So it's just the vector that looks like this. As I said, the TQDM showed us the progress bar with some non-finished total number of iterations, because the MNIST loader also implements the len method, so we can use the len operator to find the total number of batches in the loader. And to have some examples, we could use the batch we have, the images batch, take the first example, take the first channel, as just grayscale image, convert it to NumPy, and show it like this. And here the target that this is obviously is A7. Okay, so now we have the data to work with. We have the data loaders that gets the tensors, and now we need to pass those tensors somewhere to have the outputs and to train our models to get some predictions and so on. So for the built-in models, there is some abstract torch NN module class that used to implement all the torch models to train, to use, and to use for predictions. And this torch NN model has lots of some built-in bricks to build our networks with several layer classes. For example, we will use it later. And also there are some functional version of those models, so not the built-in models, but just pure functions to use as the layers. For example, if we have to do max pooling, we could create the max pooling module and use it for inference, or we could use just the functional max pooling method we have. The same goes for the upsampling and rectified linear unit. So we have the module that we can combine to create some more complex models, or we can just use the functional version of this method. Also, there were previously the upsample modules. I think they actually might be already back in the current versions, but before that they were deprecated, and it was recommended to use the new interpolate method. And for composing several building blocks, for example, we could use the NN sequential item to build the sequential method from the block. For example, we could use the sequential blocks that are used in ResNet model. So we need to create several convolutions and several rectified linear units like this. So, and we just use the sequential to concatenate all those models in sequential way. And if we print it down, so we have some sequential model that consists of convolution, ReLU convolution, and another rectified linear unit. And after we created some complex model for touch vision, we could start training the models. So the basic pipeline looks like this. So we have the model, we have some torch tensor. So actually we will have some torch tensor from the data loader. So we have some target, we have some criterion. For example, this is the squared loss. For binary segmentation, we'll use the logistic loss, and we calculate the loss based on the output we have and the real targets we have. And after this pass is done, that parameters of the network will have the gradients to use for updating. So we could use the manual updating like this, but actually for the real world optimizations, there are several submodules in Torch, like Torch Optim family of submodules. For example, we could create the stochastic gradient descent optimizer like this. So we have the network, we have some parameters we need to update. So we have some learning rate, and we create the stochastic gradient descent optimizer for these parameters. And for each step, at first we just nullify the gradients we have on each iteration. It's not done automatically because some techniques propose maybe several iterations before doing the gradients before the optimization step. But you can do it manually on each iteration to do the training in some common way for classification models. So the training step will look like this. So we have the output from our network, we calculate the loss, and to propagate the gradients over the network, we just create the call the backward method to do the backward propagation. And to update the model, we just call the optimizer that we created previously. So we have the optimizer stochastic gradient. After the loss backward is called, the network parameters has the gradients in it. So we just use the created optimizer to just make a step based on the gradients we have for our parameters to update the parameters. And to update the optimizer in some way, for example, in ImageNet training, the schedule for training looks like we have the initial stochastic gradient descent with the learning rate of 0.1. We train the network for 30 epochs. After that, we update the optimizer to decrease the learning rate by the factor of 10, so it becomes the 0.01. Then we do another 30 epochs. So we run all the images in ImageNet 30 times. After that, we again decrease the learning rate by the factor of 10 and do another 30 iteration, 30 epochs. Then we another time decrease the learning rate by the factor of 10, and we finish with another 10 iteration, 10 epochs of the training. And to create such a schedule, there is a submodule called learning rate scheduler in the Touch Optim module. So we could create the step scheduler, so it works like the schedule I've mentioned for the ImageNet. So we have the step size and the gamma. So after the 30 epochs are done, so after the scheduler stepped 30 times, the learning rate of the optimizer is decreased by the multiplying on the 0.1, so by the decreasing it 10 times. And the training ResNet on the ImageNet will look like this. So we have 100 epochs. We use the training step, then we do some validation to plot the loss curve and the accuracy curve, and then we apply this step for the scheduler. So, and basically just has three these options. And before that, we call in some previous PyTorch version, we use the scheduler step before the training validation, but in the modern PyTorch version, you should make it like this. So train validate, and only after that, you should call scheduler step. If you are doing it correctly, you will have a warning in the console. And also there is an option to call the scheduler step with the epoch as its parameter, but it is also deprecated. So you should just call scheduler step without any options. And to restore the current epoch to resume the training, you just resume the scheduler state from some checkpoint, and not by you calling it in this implicit way, explicit way of just calling the passing the epoch as a parameter. So you just should call it without any parameters. Okay, so this is the brief overview of the training scheme for just pure PyTorch way, but there are several libraries out there like PyTorch Lightning, Kekas, Catalyst, and others that can help you to build the training validation pipelines for your models. So as the part of home task, the optional bonus points, you will get them if you use some of these libraries to create more simpler pipeline for your home task. Also, the same states for the augmentation libraries I've mentioned earlier, like augmentations. If you use them for the training pipeline, you will get some bonus points for your home task. Okay, so we'll overview some simple bricks for our models, some simple training procedure to train the models. So let us build the real model based on our knowledge that we have now. So the model we will going to build is the UNet model. So to recall the UNet model, it looks like this. So we have the several encoder blocks, and we have the decoder blocks. Each encoder blocks consists of several convolutions and the downsampling that is implemented via max pooling. And also we have some decoder stages with the decoder blocks, and each decoder blocks consist of several convolutions and upsample plus convolution to upscale the image, to upscale the feature maps we have. Okay, so let us try to build this model. So one of the basic brick for this model is those convolutions that every convolution is has the kernel size of 3 by 3. So we just implement the const3 by 3 function to build the convolution module we need for building our network. And let us try to build one simple encoder block that looks like this. So the encoder block will have the convolutions and rectified linear unit, convolutions, and another rectified linear unit. Optionally, if, as we know, the unit is based on VGG, there are VGG variations that use the batch normalization for, after the convolutional layers. So we will add the batch normalization flag. So if the batch norm is true, we'll add the batch normalizations after the convolutions we have. So actually this encoder block, it implements these two sequential convolutions that we have in the encoder stage. And also in any module, it must implement, the only method it must implement is the forward method from the input we have. So X is some tensor, and this tensor X is passed into a module, and we need to calculate the output based on our modules we have. So we just sequentially use all the models we have in our encoder block. So we just call the convolutions, rectified linear units, and optionally batch normalizations to output the resulting tensor here. Okay, so let us build some encoder block. So it will look like this. So it has convolutions and rectified linear units because we didn't use the batch normalization here. And we can just run the inference for some just zero tensor base 0, so the size needed. The typo. Okay. So this is instruction with torch norm gradients. It calls the torch library that we don't need to store some intermediate information during the forward pass to use it at the backward pass. Thus, we will speed up the inference and we will take less memory space for this procedure. So, for example, if you just make the normal forward pass for the training purposes, then you need to store some information for all your modules in the network to apply the backward propagation after that. For example, you will need to store the positions for the max pooling operation to pass the gradients backwards just for the places that were maxed on the forward pass and like this. So we will apply this thing to increase the speed and decrease the memory space needed for the inference. Okay, and the output looks like this. So we had the three channels in the input, and we had the size 128 by 128. So the output will have the same size, the same batch size, obviously, but we have a different number of channels for our image. And there is just another alternative for the definition. So here we just implemented the some methods as the part of the module, but we could just create the sequential module and wrap it into the encoder block. Just add modules to our sequential module. And just on the forward pass, we could call the sequential block we have in this encoder block encapsulated. And the result will be just the same. Also, we could create some functional versions. So we could create the encoder block function that will create the encoder block for us, and that is will be actually just sequential module with some blocks applied to it. So encoder block is just some building function for that, but the result is also the same. Okay, so now we have the encoder block that looks like again like several convolutions, and we need to build the encoder that is based on the several encoder blocks and several downsampling operations. And as the forward operation for the encoder, we need to pass one encoder block after another with the downsample operations between those passes. Okay, so the encoder looks like this. We have some number of input channels. So for the RGB images, we have 3 input channels. We have some predefined number of filters in the first encoder block. So for example, it is 64 for the UNet model originally. And we have a number of blocks to build. For example, if we want to use 4 blocks in our UNet module. So we store the number of blocks, and for the and iterate over this number, we calculate the number of input channels and number of output channels as, with the multiplying by the 2 powered in some degree to have even more blocks on the bottom layers as we decrease the resolution and increase the number of features. And we add some modules, and we create the pooling modules for each block, but last one. So we don't need the pooling after the last encoder block. And as the forward operation, then we could just use these created blocks to call it with our tensor, and we store all the preliminary outputs. So as you remember, we need all the preliminary outputs of our encoder blocks to store them, to concatenate them later with the decoder blocks on the decoder stage. So we pass the input tensor to the encoder block, we store the output, then we call the pooling operation. After that, we apply another convolutional block, encoder block, and store the output also. So at the output of this encoder, we'll have the list of preliminary outputs on the encoder stage. Yeah, so if we create some simple encoder, it will look like this. So we have sequentials sequential as the encoder block. Then we have max pooling. Then we have another block that is actually a sequential module. and so on. So we have different encoder blocks and max-Pooling operations between different encoder blocks. And if you pass some tensor like this into encoder, we will see the different preliminary outputs of the encoder stage. So we start with 8 features and 500 sized images. Then we decrease the size of the image and decrease the number of filters on the encoder stages. And now we must use those preliminary outputs of the encoder stage to pass it into the decoder and to have the final probabilistic map for as an output for our task. Yeah, so at first we need to create the decoder block. So I will just use the new upsample module, but you also could create the custom upsample module and some of the PyTorch versions. So the decoder block, it consists of the upsampling comparison to increase the dimension of to increase the resolution of our image. Then we apply some convolution to improve the quality of the upsampling optionally. And then we apply two convolutions like in the inverted VGG. So the decoder block is just use the pulling from something that come from down. Then we apply the convolution for that. Then we concatenate the output of the upsampling that comes from the down of our network and concatenate it with the left output of the encoder block. So actually, that's what just happens on the UNet image. So we have the X that comes from this bottom of the image. Then we have the convolution that applied to it. Then we concatenate it with the output from the left from the encoder block. Then we have two convolutions. And then we apply this block again on the next stages on the encoder. Okay, so the forward looks like we have the pooling, upsampling. We have the convolution to improve the quality of the upsampled image. We have concatenation and then several convolutions and the result of the second convolution is the output of our decoder block. So let us create the decoder block. Let us imagine we have some output from the encoder. So we have the output of this small encoder like this, and we need to apply the decoder with this thing that came from the left and this thing that came from the bottom of the network. So we apply this block with these outputs and have the output for the next decoder block. This warning is for the upsampling model because there are different behavior for the upsampling in different version of PyTorch. So since 0.4, the behavior has changed and you should manually use the align corners parameter to use it explicitly without using the default align corners parameter. So this is not a big deal, but anyway. Okay, and to build the decoder, you need to use several decoder blocks and call them one after another. So there is nothing between those decoder blocks. We can just use several decoder blocks and store them as the submodules of our module. And on the forward pass, we iteratively just use something that came from the bottom and something that came from the left and call the decoder block from those two tensors and iterate over such decoder blocks and iterate over the activation of the encoder stage. Okay, so if we have some encoder, so we have 4 outputs of the encoder, and then we can pass these 4 outputs of the encoder into the decoder to get the final tensor. So if we just call like this, decoder from the X, and we'll have just one tensor as the output with the desired size. So at the end, we just need to apply some convolution to get the number of classes that we need for our task. So finally, we can build the UNet network. So the parameters have the number of classes, the number of input channels, that is 3 for HB image, the number of filters is 64 for the default UNet, and the number of blocks is 4. So we create this UNet network as the encoder, the decoder, and we have some final convolutions to make the final classification in the full convolutional way. And as the forward function, we just have the encoder, we call the decoder, and we have call the final convolution to make the final output. So I left this piece of code as the some old school way. So if you see these instructions like variable in some PyTorch codes you found on the GitHub or anywhere, and you can see some instructions like this with variable and volatile. So the thing is that before the PyTorch 0.4, there were different entities for the tensors, for just pure tensors that are used for the inference, and the variables that were kind of the tensors that has some graded information in them. And by default, if you created some variables, so you could use them for training. And if you need to create some variables for the inference, then you could create it like this. So you have some tensor, you convert it into the variable, and you pass the volatile parameter. So there will be no storing of gradients, just like the torch no grad instruction I used previously. But if you use such a legacy code in your modern PyTorch version, then these instructions, this and this, they will have just no output at all. So if you create the tensor like this, it will be the same simple tensor. And if you use this instruction, so the instruction will take more time and more memory because you will have the torch tensor with gradients in it. So if you see a code like this, you must upgrade it to the newer version that, for example, will look like this. So instead of all those variables and volatiles, you will just use the torch no grad instruction to forward pass your images for the just pure inference. Also, instead of using all those CUDA methods, if there is a CUDA available and so on, you can just create the one device that is no new entity starting from the PyTorch 0.4. And you could use this device to pass all the models and all the images you have to that device. For example, if you had the GPU, both the model and images will come to the GPU for the faster computations. And if you don't have the GPU, then the device will be CPU, and both those instructions will do just nothing. It will take some time. Okay, so now we have some UNet, then we have the images that are actually tensor, we pass it to the network, but as you know that we actually need some probabilities at the output, but instead of using creating probabilities, we can just use the raw output of our model without the softmax or sigmoid or something layers, and just use those pure output with some special loss functions that in PyTorch they have the with logits suffix. So we just pass the raw output before the sigmoid or softmax to the this loss function. So you pass the raw outputs and the labels, and after that you calculate the loss and do the backward pass, and it will be the better way than creating and calling the softmax and sigmoid at first, and then creating the loss with the probabilities and the general logistic regression function, logistic loss. Okay, so as we've built the UNet, we could use the UNet structure we have, and we know that this encoder, it was actually built just like the VGG network without the last classification layer. So actually looks like VGG11 without fully connected layer at the end. So if we have the UNet module, and for example, we want use it to solve some general task like portrait segmentation, we know that VGG, we have the VGG weights that were trained on the ImageNet dataset, for example, and we can use this VGG to predict whether there are people on the image. So it is natural to use this pre-trained VGG network without the final fully classification layer as the encoder in our UNet network. So the encoder would be already trained to find people and persons on the image. So we will create the portrait segmentation. To create the final portrait segmentation, we only need actually to train the decoder stage, and it will make the training procedure faster for the desired quality and desired output of the network. So we want somehow to reuse the already trained VGG network to improve our quality and to make the training faster. Then we can just use the pre-trained VGG actually from the Torch Vision library. So again, the VGG architecture, it looks like this. So actually, until these blue stages of fully connected layers, so this is basically just the encoder stage of the UNet. So we can reuse this thing in our network to improve the speed of the training. Let's just use the Torch Vision library again. So there is a model submodule with several network implementations, like for example, VGG13 network. So we can build such VGG network without using the weights, and it will look like this. So you can see that there is a features submodule in VGG and the average pool and classifier submodule of it. So if you just use the features submodule of VGG network, then we'll have just what we built previously. So this is the sequential of several convolutions, rectified linear units, and max pooling operations. So we will use it to implement the encoder. So we will call it VGG13 encoder that is based on VGG that will act just like the encoder for the UNet we've built previously. So we use the backbone of the VGG, so only the feature spots that we need. So we can use the pre-trained flag to download the VGG13 weights for our model and for the VGG13 model. So the encoder will be already pre-trained for the task of any segmentation for the classes that are present in ImageNet dataset. So for the number, for the range of the blocks, we will use the block that is built as sequential of several sequential blocks of our backbone. So we could see that the VGG features that they're just one big sequential module of convolutional rectified linear units and max poolings. But in our architecture, we had these layers grouped into some blocks. So we had the block from these four modules, then we have max pooling, then we had another block of these four modules, and so on. So for this VGG encoder class, we will use the four sequential blocks from the VGG to form the encoder block just we had in our previous implementations. And after that, we will just reuse the max pooling. So actually, there is no need in reusing it. We can just build another one because it has no weights stored in it. And the forward pass, it will look just like the encoder we had previously. So if we build the encoder based on the VGG, it will look like this. So we have the block one that is sequential of four layers like convolutionally rectified linear unit. We had max pooling, another block, and so on. And if you compare it to the encoder we had previously, you can see that they are basically just the same. So it is block of four layers, pooling, block, pooling, another block. And all the numbers on the features are the same. So actually, instead of just creating a vanilla encoder for the UNet from scratch, we can just reuse the VGG as the encoder, and we could use the pre-trained equals true, and it will start to download the weights for the VGG network. Okay, so and after that we will have all the weights in the encoder that are already suitable for any common task we need to train. Okay, so as for the home task, you need to create the dataset for some toy dataset. So you will need to implement the dataset that will output images like this. So some ellipses, some random ellipses placed on the image with some random color and the noise applied to the images. And you will also output and generate the ground truth for such an image with all the ellipses, true ellipses position. And you will train the module on this toy dataset to have the output prediction. So you can see, for example, that for this image, the model will, had difficulties with segmentation of this blurry circle, and it never found the image that was here on the ground truth because it actually just the same color as the background. So we'll need to create the ellipsis dataset, and based on the your surname, we will find that you will have to implement one of the two papers for the semantic segmentation models. I actually will replace these modules with more recent one before the uploading, and I will publish to the Telegram channel that the home task is ready as for now. And you will implement those modules with some custom encoders. So basically in those papers, you will see some semantic segmentation models like we described earlier on the lecture, and they will use the ReasonNet backbone. And you have to implement those models, but instead of ReasonNet backbones, you will need to use some custom backbones like DenseNet or DPN models. So DPN is dual path network. Is just another classification models. I could replace them with some more recent, maybe two, but basically the task will be the same. So you will have several custom segmentation models to implement, and instead of the backbones proposed in the paper, you will have different backbones that you must use in your paper. And after you've trained the yeah, so and for this training, you will have the TensorBoard used for the output of the loss curves and some images and preliminary segmentation maps you will have during the epochs of training. And after you finished with this toy task of ellipses, you will need to solve the actual real world task of portrait segmentation. I've prepared the easy to use dataset for you that is stored on the Yandex disk. And you will train the segmentation models for the portraits. So it's just like binary segmentation for the persons on the images. Okay, and there are another bonuses for this task. So you could get bonus points if you use Augmentations library or Imago library. If you use some custom frameworks for building pipelines like Peterslide and others. Also, you will have bonus points if you create and deploy the actual demo for your model that will look like this. So you could visit this GitHub repo, and there are links for the demo that is already published on some website. So we will need to, for these bonus points, you will need to register the email domain that is actually free to register with the free nom registrator. And you will have to just use some free credits from the Amazon GCS or something like this that are enough for the deploy and demo for some period of time. And as the MMP group, they actually had some tasks like this previously. They will have additional points that will be a must to accomplish the task. So you will need to integrate the mixed precision training that is available starting from PyTorch 1.6 with half point precision. So they are linked to the dogs, and having the demo deployed from some amount of time is also a must point for you. So, and you could also get bonus points if you do it earlier than this period. So I think this is all for today. If somebody have any questions, you're free to ask in chat or in audio.
Okay, can I ask a question about the deployment? We should use Amazon Web Services for this, or what?
Yeah, you could use any cloud provider like Amazon Web Services or Google Cloud or Azure ML from the Microsoft. So actually, all of them have some free credits, like for 200, 300, or $400. So if you use just the smallest, I think, instances, that this will be enough for that, for deploying the models. And actually, you don't have much work to do for the creating the web service and others. So if you look at the repo I've mentioned here, so all you can do is just replace the UNet model present in this repo with your own model that will output the probabilities for the portrait dataset in the task. So the demo is already published for the task of the portrait segmentation. So if you just replace your model with the model and the repo with your model and publish it, so you will get the demo running. Okay, so if there is no question left, so I think that's it for today. Thank you for coming, and you're free to write any further question into the Telegram channel. So the home task will be updated and pushed to the repo before Monday, I think, and the deadline will be, as usual, you will have 2 weeks to accomplish this home task.